have fallen into Event Horizon with John Michael Godlier. Jonathan Gorard is a research mathematician at the University of Cambridge, an algorithms R&D consultant at Wolfram Research, and one of the principal researchers on the Wolfram Physics project. His work lies at the intersection of mathematics, physics, and computation, with interests ranging from mathematical, logical, and computational complexity to general relativity and the foundations of quantum mechanics.
Jonathan Gorard, welcome to the program.
Hi, it's great to still be here.
Yes. What predictions does the model give us about the universe?
Ooh, okay, interesting one. So one of the things that's important to clarify here is the distinction between a particular model and a class of models, right? So what we've developed so far is a formalism. It's a class of models as opposed to a specific one. So asking whether the formalism, whether this sort of infinite class of candidate universes, whether that in itself makes predictions, it's a little bit like asking if calculus makes predictions or if differential geometry makes predictions. It's a category error, right? The formalism is not the theory. The theory is a particular rule, and obviously we haven't yet succeeded in finding the particular rule for our universe. So it's important when asking about predictions of these kinds of formalisms to bear in mind that's not generally what formalisms are for. Once we find the rule, if we find the rule, then of course it will. Then we'll have to start making predictions, and we'll have to start comparing those things against experiment and against observation. But that being said, one quite remarkable thing is how much of this formalism, how much of the features of these formalisms are actually generic, and because of that fact, we can start to make somewhat tentative predictions already, even without knowing the specific details of the rule. So I already kind of alluded to one of them, which was this stuff to do with quantum information theory. So if our interpretation of quantum mechanics is correct, in the sense that it's to be interpreted in terms of these multi-way systems, all these different branches of history kind of occurring in parallel that kind of merge and split and do all these crazy things, and that somehow the parallelism of that is responsible for giving the speed up of quantum computation. If that interpretation is right, and if our interpretation of measurement is right, and measurement being this computational process that has its own laws of complexity associated with it, then that makes certain predictions about efficiencies of certain classes of quantum algorithms that might conceivably be testable experimentally with real quantum hardware within the next few years. That's something I'm really quite excited about, because even though it doesn't test the whole model, it does test a major feature of it, which is, as I say, this particular interpretation of quantum mechanics. There are also certain features of the derivation of general relativity that make fairly generic predictions about things like cosmology. So Stephen and you guys already kind of discussed the expansion of the universe that occurs as a result of these network substitutions. One thing that we didn't really discuss is that in standard general relativity, one assumes that the dimension of space and the dimension of space-time is always the same, 3 and 4 respectively, and it's kind of the same everywhere for all people. But because we have a network, and because the structure of a network is much less rigid than the structure of space or space-time, it turns out the dimension of the network can change over time. It can change globally and it can change locally. And in fact, global dimension change is a very, very generic feature of these models. In many instances of them, basically start off with very, very high dimensions, with very high network connectivity. And then the network connectivity becomes progressively more sparse, and so it kind of converges down to something much lower dimensional. And one of the consequences of that is that the universe ends up being much more causally connected than you would conventionally expect in cosmology. And in fact, we were able to compute that a universe that underwent this kind of global dimension change would have the process of global dimension change would have observational consequences that were very, very similar to the standard inflationary model of cosmology in which the universe expands exponentially, at least in its initial phase. But it also introduces certain other predictions that are not made by inflation about there are certain predictions about gravitational wave signatures and signatures in the cosmic neutrino background about that kind of indicate that a global dimension change occurred. And those might potentially be observationally measurable. There are sort of astrophysical predictions that are quite generic. Again, as Stephen mentioned, this notion that space, physical space and branchial space kind of become mixed up when you get close to a black hole event horizon. And the fact that event horizons exist both in physical space and in branchial space both gives you kind of Hawking radiation, and it predicts certain resolutions to the black hole information paradox. That's again a fairly generic kind of astrophysical feature of the models that could be experimentally tested. So it's the really exciting thing is there are a bunch of avenues for potential experimental and observational tests, even though we haven't yet found the rule, which is really quite surprising.
Now, how does gravity, which of course has confounded Einstein? I mean, he spent the last 30 years of his career trying to come up with a quantum theory of gravity. How does this fit in? What does your model say about gravity?
Yeah, okay, that's a great question. So the story is both very simple and very complicated, depending on how you look at it. So Einstein's theory of general relativity, which is our current best model of gravity, is a purely geometrical theory. It says that energy and matter tell space and time how to look, and space and time tell energy and matter where to go. And this is summarized in the system of equations called the Einstein field equations that relate the Einstein tensor, which is a measure of curvature of space-time, to this thing called the energy momentum tensor, which is a measure of the kind of energy matter content of space-time. And it represents the coupling between the two. So a big question was, can we reproduce the Einstein equations with our model? The answer turns out to be, rather excitingly, yes, we can, kind of in complete generality. And the way that it works is, okay, so imagine you have one of these networks, and you want to work out how many dimensions of space am I in? Am I in one-dimensional space, two-dimensional space, three-dimensional space, whatever? Because of course the network only has information about connectivities between points. It doesn't tell you anything about the dimension of the space in which it's immersed. But nevertheless, you can approximate how many dimensions of space you're in, because you can start from a point in the network, and then you can look at all the points that are adjacent to that point, and then you can look at all the points that are adjacent to those points, and so on. And you can grow out this ball of kind of size r. And you can ask, how do the number of, if we go out a distance r, how do the number of points enclosed within that ball grow with the distance r? And so, if you're in flat space, it's going to grow roughly like the area of a circle, pi r squared. If you're in, if you're in two-dimensional space, that is. If you're in flat three-dimensional space, it's going to grow roughly like the volume of a sphere, 4/3 pi r cubed. And in general, in sort of d-dimensional space, it's going to grow like r to the d. And that turns out to be exactly correct if the space you're in is flat. But if it's curved, then there's a correction term. And the correction term, if you compute it, turns out to be proportional to this quantity, which is called the Ricci scalar, which is a term that appears in the Einstein equations. So that's already quite encouraging. Then to really to do the full derivation, what you have to do is you have to then go to these causal networks. You have to look not just at the spatial network, but actually at the space-time network, which shows you all the causal relationships between all the different events that have happened. And then you can ask, well, how many dimensions is the causal network? And so now you're growing not a ball, but you're actually growing a space-time cone, but it's still the same basic idea. It still grows like r to the d with some correction term. And this time the correction term is a slightly more complicated thing. It turns out to be proportional to a time-like projection of this thing called the discrete space-time Ricci tensor. But then if you make the assumption that even if as I mentioned, the dimension of your space-time can vary, and it can bubble around, and it can start off very high and it can converge down low, as long as you make the assumption that it eventually converges to something fixed and finite, like 4 dimensions, then that implies certain conditions, it implies certain constraints on the Ricci tensor. And if you compute what those constraints are for the network case, they turn out to be exactly the Einstein field equations. The Einstein field equations are the most general set of constraints that are needed to ensure that you have a causally invariant space-time that limits to something of fixed dimension. And so then what that implies is that if you have energy, if you have matter, if you have regions of high activity in your network, they are compensated for by apparent curvature of the network in the surrounding regions. And that leads to curvatures of geodesics, and it leads to the appearance of gravitational acceleration. So it's remarkable. Again, it's one of these things that's like you start from something incredibly simple, but just from making very, very small assumptions, you can derive this huge feature of our universe, which is gravitation.
Does the model give any insight on questions of other universes, previous universes, or the many worlds interpretation? Does this give us any clue there?
Yeah, okay, that's a cool question. There are many different kinds of multiple universes that you might think about. And it's important to make the distinction between the two. I think that there's even a kind of hierarchy of multiverses that sort of exists, right? So there's, let me start with the kind of the least controversial and then extend up to the most controversial cases. So in ordinary physics, one sense in which there can exist multiple universes is because we have an expanding universe, and we all exist in a little sort of observable patch of that universe. We can only see about, the radius of our observable universe is only about 45 billion light years. And there's a thing called the particle horizon that exists a little bit beyond that. And basically that's everything we could ever observe or interact with. Because if we tried to go beyond that, or if we tried to observe something that was beyond that, the expansion of the universe would be so rapid that it would involve us going faster than light. So effectively, the particle horizon gives us the limit of what are the things we could ever see or interact with. And so in some reasonable sense, you could say that's our whole universe. That's the set of things about which we can actually observe. But we don't say, oh, but there can't exist anything outside that, right? It'd be like being in a ship in the middle of the ocean and looking at the horizon around you and saying, oh, well, there can't exist anything beyond that horizon because I can't see it. That's kind of not, generally in science, if the model you have makes good predictions about the things you can see, then you sort of take seriously the predictions it makes about the things you can't see. And so most people would agree that there exists stuff outside of our particle horizon. So in some sense, those other particle horizons that exist out there that we can't interact with, those are, in a meaningful sense, other universes. That's a fairly uncontroversial case. There's a slightly more controversial case, which is other big bangs. This is a prediction that gets made about in modern cosmology. So in this inflationary model that I mentioned earlier, one of the issues with inflation is that it's quite hard to get it to switch off everywhere at the same time. And there's always a kind of, if it switches off in one place, it doesn't mean it has to switch off in another place. So even though inflation is switched off in our part of the universe, it might still be switched on in a different part of the universe. And this is the thing called eternal inflation, which effectively means that there could be big bangs going on kind of all over the place all the time. And so each of these is its own bubble universe that's a kind of higher level universe than the one I mentioned earlier. That's a little bit more controversial, but still relatively uncontroversial. Then there's the many worlds thing that you already mentioned, which is a very different kind of multiple universe idea, which is that in quantum mechanics, one interpretation of quantum mechanics is that there are many, many possible evolution histories for the universe, and they all and they interact and they interfere, but each one is kind of is an independent world in its own right. And this is the interpretation that was developed by Hugh Everett and has been sort of championed by people like David Deutsch. And each branch of quantum evolution history in that model is thought of as being a different universe. And then you can go even one step above that, and you can ask, well, even if we accept the cosmological multiverse, we accept the many worlds universe, all those things, could there be a higher level multiverse where it's like there's a whole other completely disconnected universe with completely different laws of physics that's sort of totally parallel to our own? And that's somehow the most controversial. Okay, our model has things to say about all of these different cases. So in the kind of cosmological case, one of the predictions, I think actually Stephen mentioned it towards the start of this thing, that one feature that often happens is you can have spatial networks that disconnect from each other, and once they disconnect, they can't then reconnect. And so once your spatial network is disconnected into two separate spatial networks, they basically evolve like completely independent universes. And similar things can happen in the causal network. The causal network basically splits into two independent spacetimes. And this is like the analog of the cosmological multiverse. And so this is perfectly consistent with our models. And in fact, it's a fairly generic feature. So our models are definitely consistent with the existence of a cosmological multiverse. They're also, as I kind of alluded to, they're also consistent with the many worlds interpretation of quantum mechanics. If our current model of quantum mechanics is right, then it means that there is in fact a multi-way system. There is in fact a collection of different evolution histories for the universe, and they do indeed merge and split and interact and do all these other kind of things that are predicted by the many worlds interpretation. And so again, our model predicts that it is indeed meaningful to say that each branch of the multi-way evolution graph is itself an independent universe, is like a parallel universe. But then, okay, what about the ultimate question? What about, could there exist a universe with just completely different physics? Well, okay, this this is where it necessarily becomes a little bit philosophical. But actually, and this I have to make it clear that this is unlike the things I just said, which are fairly kind of definite features of our formalism. This is a complete kind of speculation that Stephen and I have discussed for a little while. But one of the things we think that may come out of this formalism is that actually it predicts that there can't be other totally disconnected universes, that in some sense, even though there are parallel universes in quantum mechanics and there are parallel universes in cosmology, still, if you take the whole thing, that has to be it. There can't be anything outside of that. And the reason is because it's effectively because of this universal computation idea. It's because if our universe is ultimately computable, then at some level there is only one law of physics, and that law of physics is that our universe is a computer. It's a Turing machine, and everything else is just encoding. Everything else is just the sort of the packaging, the simulation packaging. But the underlying dynamics are just given by the formal specification of a Turing machine. And if that's true, one of the implications this has, and we have this sort of scheme for thinking about this systematically that Stephen calls ruleal space, effectively the space of all possible rules for the universe. Each observer is they're plying their own course through ruleal space. Each observer is slicing ruleal space in their own way. They each have, everyone's own internal representation of the world maybe subtly different. Everyone might have a slightly different interpretation of the observations that they're making, of the things that they're seeing. So in other words, even though the underlying rule for the universe is computational, people's encodings of what's actually going on could be vastly different. And if that's true, then that means that, in some level, you and I already exist in independent universes because even though we're seeing the same universal computer, we can construct completely different encodings and completely different interpretations of what we're seeing, so that it's at some level it's meaningful to say that we're already inhabiting completely separate realities. And so if that's true, if that really is what's going on, then it means that at some level, all of these different interpretations are equivalent. And so, at some level, there is only one universe because there is only one model of computation that we're interested in, which is this Turing model of computation. And so the ultimate prediction of this model may end up being that actually at some level there has to be just one universe, at least at that abstract level. But that's a philosophical speculation that I'm probably unqualified to make.
Now, Jonathan, this begs a question. Simulation. What is your personal sense of this? Is this a simulation? Since you can describe the universe with a computer model, is it really possible that maybe this is all just a simulation by something, whether it's a Boltzmann brain or something like that? Is it possible?
Yeah, okay. So I have possibly somewhat heretical views about the simulation hypothesis, in that I think it kind of misses the point, right? So when people were developing the sort of foundations of mathematical physics back in the 1600s, for instance, it's entirely plausible, and in fact people did this, that they would say, that Newton's equations, or later Maxwell's equations or Einstein's equations or whatever, they successfully describe the physical universe, and therefore our universe must just, quote, be mathematics at some level, right? It's like that I think is that's a metaphysical leap that I think is completely unjustified, right? It's confusing the description language, in this case mathematics, for the actual ontology, the actual reality, right? Saying mathematics describes the physical universe is not equivalent to saying, therefore, the universe is just mathematics in some sense. And the same philosophical error was kind of made with computation, right? So as it became increasingly clear towards the late 20th century, early 21st, and with the work of people like Stephen, that that it was useful to think about the universe in a purely computational way, that this was a fruitful paradigm for doing basic science. Many people made the leap of saying, computation is useful in describing the universe, therefore our universe is a computer in some sense, right? It's exactly the same philosophical mistake that people made back in the 1600s. And I think it's wrong for basically the same reasons. Now, and that's kind of, that's the thing, saying therefore the universe is a computer kind of misses the point. The point is that is actually something much deeper. It's that the notion of computation universality means that, which formally in mathematics is called this thing is referred to as the Church-Turing thesis. What it basically says, I think, is that a computer is a physical system that instantiates the abstract notion of computation, via kind of a concrete physical process. So in other words, the notion of computational universality means that if you take a universal computer as a physical system, the set of motions that physical system can undergo is in one-to-one correspondence with the set of motions that any physical system in the universe can undergo. That's a much deeper, but also more subtle point that I think has actually been largely missed in the kind of philosophical debate about what computation really means. In addition to saying that I think it's kind of a philosophical misstep, there's another reason why I'm a bit skeptical about the whole simulation idea. And that is this thing that Stephen alluded to, which is computational irreducibility. And in particular, okay, this is a mathematical result that I kind of worked on and proved various theorems about a couple of years ago, but I'll try to sort of simplify the basic idea. But, okay, so suppose we have an algorithm, a computer program that successfully reproduces all of the physical universe. Let's call it P for program. And if it correctly predicts the behavior of everything in our physical universe, then one feature of our universe is we know that we can build computers. We can build universal computers that can simulate any other universal computer. So in particular, this algorithm, and I should say, those universal computers are themselves physical systems. And so if this program P predicts the behavior of all physical systems, it should also predict the outcomes of all computations that are done by these computers. So now imagine that you take your program P and you implement it into a computer within the universe. And you write a program that basically says, if P predicts that the outcome of this computation is going to be X, then make the outcome of this computation be Y. Otherwise make it be X. Well, it's like now you have a physical system, namely this computer, which by its very construction contradicts any predictions that get made about it by this program. Okay, that seems a bit disastrous, because then you might say, well, therefore it can't be the program for our universe. But actually, there's a more subtle get out, which is that it could also just be the case that by the constraints of the universe, it's not possible for this computer to kind of shortcut its own computation to predict what the outcome of its own computation is going to be before it itself sort of has finished computing it. And so you naturally end up with a situation where you predict that the universe's computation must therefore be fundamentally irreducible. And so this is a way you can kind of prove a lower bound for the computational irreducibility of the universe. Now, if that's true, it places a lot of constraints about the simulability of physics, because although it's possible in principle to simulate our universe, it's that the constraints of our universe are such that that any such simulation will necessarily take more time than the universe itself takes to evolve, because otherwise you could shortcut the process and you could get this contradiction. And given that that's true, it means that the scientific hypothesis or the philosophical hypothesis that, quote, the universe is a computer or the universe is a computer simulation cannot have any predictive power, because in order for it to have predictive power, it would need to make predictions about the outcomes of experiments that you could perform in the future, which would require you to be able to shortcut these computations. And as I just kind of reasoned, if you could do that, then you could always construct a contradiction. So, and therefore, for me, realizing that and proving that result was kind of the final nail in the coffin for me with regards to the simulation argument. It's basically saying, yes, okay, our universe could be a computer simulation, but at some level that's kind of a meaningless and empty statement, and it's not one that can be tested scientifically. And so it's a theological claim and not a scientific one. Again, it's not one on which I feel personally qualified to pass opinion.
Metaphysical instead of physical.
Right.
Now, given the model and the predictions that you can tease out of it, we mentioned FTL, faster than light travel, and all these sort of sci-fi crazy ideas. Has there been anything, and this is my last question for you, but has there been anything that surprised you or blew your mind about predictions from the model?
Ooh, that's an interesting question. There are a lot in some sense. Faster than light travel, that's still something that's still something that's very speculative. I mean, it's something that kind of, in principle, you could kind of make it work within our models, because you could set up a network that has something that Stephen refers to as a space tunnel, which is just kind of a collection of edges in the network where those edges don't correspond to the usual spatial structure, but where they connect apparently disparate regions of space, so that if you took the space tunnel, you would appear to have traveled faster than light, even though locally you never violated special relativity. So there are features like that, and there are related things in which we can get kind of wormhole solutions and other kinds of things. But it's not yet completely clear how generic those are, or whether those are just kind of pathological cases that won't turn out to be relevant to the actual universe. It's a bit like general relativity. Relativity is consistent with all kinds of crazy things. It's consistent with closed time-like curves, and it's consistent with these Einstein-Rosen bridges, these wormhole solutions. But most people suspect that those are really just pathological features of the formalism. They're not really fundamental features of reality. And I think there's a similar thing is going on here. So in terms of the most mind-blowing kind of generic prediction that this model makes, I would have to say one of them is this notion of what happens at a black hole event horizon. That, for me, as someone who works in general relativity, works in quantum gravity, that's something that I found really quite lovely, because it made tangible. That there's this idea in sort of modern theoretical physics that essentially what happens is it's related to what's called the holographic principle of the ADS-CFT correspondence, and it basically says that when you throw something into a black hole, the reason why the information isn't lost when it then gets re-radiated is because at some level the information gets encoded at or just beyond the event horizon in such a way as to preserve both quantum mechanical unitarity and to preserve special relativity. But that's still, that's a model that still is not completely worked out within the framework of modern physics. Within our formalism, it just directly drops out. This notion that information gets holographically encoded just immediately drops out, because whenever you have a spatial event horizon around a black hole, you also get a branchial event horizon, and the branchial event horizon kind of exists strictly on the exterior of the spatial event horizon. And so when you get information that gets sent in, it gets preserved at one level at the spatial event horizon, and at a different level it gets preserved at the branchial event horizon. And crucially, Hawking radiation is emitted from the branchial event horizon. And so it gives you a way of recovering the information without that information ever having gone past the causal event horizon. And so that was a really cool sort of instantiation of this idea, for this fairly abstract idea in modern physics that I personally was not expecting to see. And, I have to say that this whole interpretation of quantum mechanics that, I'd originally proposed it as just as a thought experiment. Wouldn't it be interesting if it worked this way? It's turned out that it's given us a whole lot of predictions that are genuinely compatible with things we know about real quantum mechanics and quantum field theory. So it's looking increasingly promising and plausible that something like this is probably correct. And this interpretation that basically there are all possible evolution histories of the universe are occurring, and they're occurring simultaneously. The observer is straddling all of these different evolution histories, all these different evaluation orders of the network, and trying to make sense of what's going on. And that the interferences that they see are a consequence of their own internal representation of the world, trying to collapse down the multi-way system from all of these different branches to just a single branch. That's a really kind of mind-bending idea that links a bunch of concepts in quantum mechanics, in statistical mechanics, in relativity, and in kind of mathematical logic in a really, really elegant way. And that's, the idea that something as fundamental as quantum mechanics could work in that manner was something that I was personally not expecting. And if it turns out to be true, I think that's also pretty mind-blowing.
I must say, the elegance of it all is intriguing. We are out of time, Jonathan. Thank you for joining us today, and I wish you the best of luck in your work, and I hope you figured out the universe.
Thank you so much. Thanks so much for the invite. This is a real pleasure, and hope to talk to you soon.